Picture this. It's 2 a.m. Your pager is absolutely screaming. You scramble to log into your monitoring dashboards, and immediately you're faced with a massive, mind-bending contradiction. All your standard metrics are telling you the cluster is perfectly healthy. Average CPU utilization, resting at a cool 15%. Memory looks totally fine. But over in the customer support channel, users are reporting that the entire system is down. Your production environment is failing, but your standard metrics are literally lying to your face. Welcome to this explainer, where we're going to dissect the architectural nightmares that separate junior developers from true senior back-end engineers. All right, let's dive right in.
This brings us to a terrifying, yet surprisingly common real-world scenario. Production is failing, the dashboards look entirely green, and yet traffic is just hitting a brick wall. So why is one specific pod in your cluster absolutely burning to the ground, while the rest of the instances are essentially fast asleep? Now, a junior engineer looks at this and usually assumes, oh, there's a rogue massive request crushing the server, or maybe it's a localized hardware failure. But a senior engineer, they know better. They instantly recognize a very specific pattern of failure.
And this perfectly illustrates the exact symptoms of that panic-inducing pattern. First off, the average CPU across the entire cluster is low. What does that mean? It means your autoscaler, whether you're relying on AWS Spot instances or on-demand nodes, sees absolutely zero reason to spin up new capacity. It's basically asleep at the wheel. Second, exactly one pod is completely dying under the crushing weight of user load. So you've got this massive hotspot, but your system's automated defenses are completely blind to it.
Section 1. The silent production killer.
A senior engineer doesn't just blindly throw more hardware at this problem. They use a systematic process of elimination. Hypothesis 1. Is it sticky sessions? Are users locked to one specific server? Well, you check the service manifest. Session affinity is set to none. Okay, ruled out. Hypothesis 2. Did the scheduler just dump all the pods onto one single node? You check the cluster, and nope, the pods are spread perfectly across different availability zones. Ruled out. That leaves hypothesis 3. Protocol behavior. Are we using modern protocols here, like gRPC or HTTP/2? Because if the answer is yes, well, you've just found your culprit.
Let's move on to Section 2, the L4 versus L7 trap.
This right here brings us to a huge, fundamental misunderstanding in modern backend architecture. You absolutely have to understand the difference in how your load balancer operates. Layer 4 load balancing distributes raw network TCP connections. It routes the pipe, but it is completely blind to the actual requests flowing inside that pipe. Layer 7 load balancing, on the other hand, is application aware. It actually opens the mail, looks inside the HTTP/2 frames, and distributes the individual requests evenly right across your backend fleet.
And here is exactly why that distinction will take down your production environment: connection multiplexing. This is a core, fundamental feature of modern protocols like gRPC and HTTP/2. Instead of opening a brand new connection for every single request, these protocols send thousands of concurrent requests over a single long-lived TCP connection. So think about it. If you're using a standard Layer 4 load balancer, sure, it balances the connections perfectly the first time, but then all subsequent requests get funneled down that exact same pipe to a single pod. Your Layer 4 balancer is literally actively creating a massive hotspot.
In a typical foundational systems setup, you'll see a load balancing switch sitting right at the front, routing traffic down to the stateless workers and proxy caches. Now, traditional systems relied heavily on these front-end switches doing really simple connection routing. But as we just established, if your clients are multiplexing thousands of requests over just a handful of long-lived connections, those specific nodes processing them are going to melt into slag, while the other nodes just sit around idle. The hardware architecture itself is completely sound, but the protocol behavior totally breaks the distribution.
Which brings us to Section 3, the service mesh dilemma.
Once a team finally figures out this routing issue, their very first instinct is usually to reach for a massive service mesh, something like Istio or Linkerd. But a senior engineer is going to hesitate here. Why? Because introducing a full service mesh adds significant latency overhead. We're talking usually 1 to 3 milliseconds per network hop. In a highly distributed system where a single user action might trigger thousands of internal RPC calls, that latency cascades fast. Plus, the operational complexity is just massive. Honestly, you shouldn't introduce a service mesh unless your traffic volume strictly justifies that heavy cost.
So what are the pragmatic senior level fixes? First, use a proper Layer 7 ingress. Grab Nginx or an application load balancer specifically configured for gRPC, ensuring traffic is balanced request by request before it ever even hits your pods. Second, implement a max connection age in your application code. Literally force your gRPC clients to gracefully disconnect and reconnect every, let's say, 5 minutes. This naturally rebalances the traffic across the cluster without needing a heavy service mesh at all. Finally, standardized monitoring. Don't just set an alert on CPU. Mandate that your services export requests per second and alert on the variation across the fleet. Because if one pod is doing 10,000 RPS and the others are doing 10, you clearly have a routing failure.
Section 4. Timing tail latency.
Okay, now that we've balanced the load, we really have to deal with what happens to the request that gets stuck. When you look at standard benchmark data, you'll often notice the average response time stays incredibly low and flat for a really long time. Everything looks great, right? But then the 99.9th percentile absolutely spikes, highlighting a terrifying truth in distributed systems. It's known as coordinated omission. Average latency metrics are actively deceiving you. If 1 in 10 user requests gets dragged into an 80-millisecond tail because of a weird network hiccup or a transient packet loss, your users are feeling the pain, even if your average response time looks like a super healthy 5 milliseconds. Listen to me, the P99th metric is the only truth.
To definitively crush this latency, you need a highly practical methodology. So, here's a 5-step plan you can literally run next week. Step 1. Instrument P99 end-to-end and set strict latency budgets. Make P99 your headline metric. Step 2. Find your top 3 contributors using distributed tracing. Find the slow spots. Step 3. Remove avoidable hops. Trim those payload sizes. Stop sending massive verbose JSON files if a compact binary format will do the job. Step 4. Add tail controls, which we'll dive into in just a second. And Step 5. Isolate and load shed before you scale. Look, if your database is failing, auto-scaling your application pods will just create a massive thundering herd that wipes the database out entirely.
And that builds directly into advanced tail controls. If a request fans out to multiple replicas, you should really consider sending a hedged request. That's a secondary request sent only if the first is abnormally slow. Just use whichever one returns first. This brutally cuts off the slow tail of the distribution. Next, remember that network physics always wins. Co-locate chatty services in the exact same availability zone to remove literal physical distance. And finally, if you absolutely must retry a request, use jittered retries with strict deadlines. Otherwise, you're just going to amplify the load on an already struggling downstream system.
Finally, Section 5, the deletion paradox.
We've talked a lot about infrastructure, routing, and latency today, but the final, ultimate truth about high-performance engineering has absolutely nothing to do with servers at all. It's about the code itself. There is a fascinating reality to the developer lifecycle. A junior developer joins a team, and naturally, they want to prove their worth. So they add 50,000 lines of code, they build wildly complex abstractions, and write comprehensive error handling for edge cases that will literally never, ever happen. But when a senior developer joins that exact same team, in their first month, they might delete 15,000 lines of code. They rip out 3 unused microservices and drop 2 heavy dependencies. The junior's commit graph looks like a massive mountain. The senior's looks like a valley. But I promise you, the senior developer is adding vastly more value.
This is what we call the art of strategic deletion. You have to realize that every single line of code is a liability. It has to be read, it has to be maintained, and it has to be debugged. By deleting redundant code and combining variations into single functions, you drastically reduce the cognitive load on the entire engineering team. You must ruthlessly eliminate premature optimizations, like having some elaborate caching layer for data that only changes once a month. Make it simple. And you have to kill your darlings. If you imported some massive NPM package, but you only use 5% of its features, drop the dependency and just write the 20 lines of code yourself.
Because ultimately, as the old engineering adage goes, the best code is the code that doesn't exist. Every function you decide not to write is a bug you never have to fix and a late-night latency spike you never have to debug. So I want to leave you with a real challenge. Next time you sit down at your keyboard, instead of asking how you can add more functionality to your architecture, ask yourself how you can achieve the exact same result by removing complexity. Look closely at your load balancers, look at your P99 metrics, and critically, look at your code base. What code will you delete today? Think about that. Apply this senior mindset to your own work and watch your system's reliability absolutely soar. Thanks for joining me for this explainer. I'll catch you in the next one.